Okay, hi and welcome everyone to this week's 1W-Minds seminar. Today's speaker is Christoph Hertrich from the University of Technology in Nürnberg. He got his PhD from the TU Berlin in 2022. And before joining Nürnberg, he has been in Brussels, Frankfurt, and London. His research interest is applying polyhedral geometry and combinatorial optimization to make theory for neural networks. And today's talk will be called Understanding Neural Networks via Polyhedral Geometry. Please.
Yes, thank you very much for the introduction and for the opportunity to speak in this seminar. That's a great pleasure. So I would like to say that if there are any questions or anything, just interrupt me anytime. I think it's better to clarify things on the spot. And yeah, so as Axel said, I'm going to talk about how to apply polyhedral geometry to neural networks to understand them better as a mathematical object. And well, the first step, if you want to understand something, is to properly define what you are talking about. So let's start with that. So I'm talking about neural networks with rectified linear unit activations. So let's look at a single neuron. So what is a neuron? It is basically a node in a directed graph. And yeah, so it kind of receives inputs from previous neurons, which output some numbers. And then on the edges, there are some weights. And then we take the weighted sum of the outputs of the previous neurons with the weights. We potentially add a bias, but sometimes we will also just ignore this because mathematically it's sometimes cleaner to ignore the bias and it doesn't make a big difference. And then we apply this ReLU function, rectified linear unit, which just sets negative components to 0 and feeds through positive components. So the overall function computed by a neuron would be the maximum of 0 and an affine transformation of the outputs of the previous neurons. Okay, so that's a single neuron. And if we look at the function computed by such a neuron, then yeah, we first have the affine transformation, which basically has a hyperplane as a graph. And then wherever this function would be negative, we just flatten it out to 0. Okay, so that's the function computed by a single neuron. And we can plug them together into a whole network. Usually we would assume that this network is acyclic and layered, like this. And there are some input neurons where nothing happens except that we feed in some inputs. And we have some output neurons which still form affine combinations of the outputs of the previous layer, but don't apply the ReLU function anymore. And then the whole thing would be a neural network, in this case, computing a function from R2 to R3. Okay, so that's a ReLU neural network, and that's the object we are going to study in this talk mainly. So this graph view is one way to view a neural network. Another way is to look at basically, yeah, affine transformations that happen between layers. So if you aggregate all the weights that are on the edges between two layers, you can put them into a matrix and you will have an affine transformation Ti. And then if you also look at ReLU being the component-wise ReLU function applied to a vector, then the whole neural network computes a function which is an alternating composition of affine transformation and component-wise ReLU activations. So that way you don't really need graphs, you just need matrices to define a neural network. But still the graph view is sometimes just nicer to look at. And then in this talk we want to talk about like complexity questions about these neural networks. So let's define what we mean by the depth and the size of a neural network. The depth would be the number of these affine transformations in this definition. So in this example, 3, which is always one more than the number of hidden layers. So a hidden layer is a layer of ReLU neurons that is not the input and also not the output. So that's just by definition. The depth is always one more than the number of hidden layers. I mean, there are other conventions, but that's the convention that seems to be the most used in the kind of questions I study. And then the size would be just the number of all the ReLU neurons not counting inputs and outputs, so it would be 5 in this case. Okay, so far so good for the definitions. Are there any questions at this point? If not, then let's quickly talk about how you use neural networks. And I guess there are many ways of doing that. And I mean, there's a reason why there are like more than 10,000 submissions to all major ML conferences these days. But like one very high level prototypical pipeline would be in the first step, you decide what architecture you use. And this you kind of do yeah, by common sense, by your experience as an ML researcher. And that means you decide what's the graph of your neural network. How many layers do you use? How big are these layers and so on. And once you have done that, you take your training data, which is like sample input and output pairs, and you try to tweak the weights of the neural network by some optimization routine such that your input-output pairs are fit as good as it gets, basically. And that's that's what we call the training process. And then we hope that once we are done with this, we will also, like on new inputs where we don't know the output, we will also perform well. That would be the idea. And okay, so that's the prototypical way of using neural networks. And here are two theoretical questions I want to ask, one for each step of this pipeline. And the first one is, once we decide to fix our architecture, what functions do we restrict to? So what functions would our neural network be able to represent if we fix the number of layers to a certain number, or if we fix the size to a certain number, or any other thing we could do to our architecture? And this question I would like to call expressivity. And then the second step is, okay, once we have fixed our architecture and we want to train our neural network, how difficult is this actually as a computational problem? I mean, on one hand, we're doing this for huge neural networks in practice, and on the other hand, we just use some heuristics that seem to be well, but we don't really have theoretical guarantees. And like my research in the previous years has focused on both of these questions. In this talk, I will mainly talk about expressivity, but before I do so, I have one slide about the training complexity, where I briefly want to basically state some results and pose some questions. So, as I said, on one hand, training neural networks is done for huge neural networks in practice, but on the other hand, there are very, very strong theoretical hardness results, even for very, very basic cases. And here are some examples. For example, if you just have one neuron and you want to know what's the computational complexity of training this neuron to global optimality, it's actually NP hard already. And if you're not, like if NP hardness doesn't, if you're not afraid of NP hardness, I have some more hardness results. So there's a complexity class called the existential theory of the reals, which is like even more difficult than NP. And training neural networks with one hidden layer is actually complete for this complexity class already. And then you might have the idea that, okay, maybe in theory it's hard, but if I fix some parameters, like let's say I just have a small input dimension or something like that, maybe training becomes easier, but also this is not true. So even for these parameterized complexity settings, there are hardness results. And these are things I have worked on in the past and basically mostly proved negative things. But on the other hand, well, in practice, we use the Haase gradient descent. Maybe we don't find the global optima, but we get really close to it. And sometimes we even find it. And even, I mean, all this was just about fitting training data, but even the generalization works well in practice. So this is kind of a big mystery. And of course, there are many approaches to explain why, even though we have these theoretical hardness results, we are still good in practice. But to me, at least, I think the overall picture is still a big open question. So why are neural networks so successful? Yeah. So I guess here we can, like, starting from these theoretical hardness results, one quest would be to actually find assumptions that are satisfied in practice and that kind of circumvent these hardness results. Okay, but I don't want to talk much more about this unless you have questions at this point. Then let's jump right into expressivity. And here I want to start with a very cute and little example, which I like a lot, which is just computing the maximum of two numbers, okay? So let's say our neural network has two inputs, x and y, and we want to compute the maximum of these two with a ReLU neural network. What can you do? Well, we look at our expression, the maximum of x and y, and we just subtract y on both sides of the maximum and add it outside the maximum again. So we obtain the same value in the end. And the nice thing about this is that now we have a ReLU expression here actually. And we can realize this with a ReLU neuron, which has a positive weight from x and a negative weight from y, and we can feed it to the output. Now, we want to add y again in the end, so what we would like to have is a direct connection from y to the output, if that's possible. And if we allow this, then we are happy, and this is our neural network computing the maximum of two numbers. Now, earlier I said that sometimes we want to impose our neural network. We want to enforce that our neural network is layered. So in this case, we cannot have the skip connection from y to the output, but what we can do instead is replace this skip connection with two ReLU neurons. So one ReLU neuron would take care of the cases where y is positive, and in this case, we would just feed it through here, and the other neuron would be set to 0. And if y is negative, then it just works the other way around. So this neuron would feed through y, while this neuron would be set to 0. Okay, so that way, with one hidden layer, we can compute the maximum of two numbers. Okay, that's cool. If we can do the maximum of two numbers, we can also do the maximum of four numbers by just using the same construction multiple times. So we take the maximum of the first two inputs and the maximum of the last two inputs. This is just the same construction as I had on the previous slide. And then for the two results, we again take the maximum of these two. And now you can observe that these two neurons, which are the outputs of the first part of the neural network and the inputs of the second part of the neural networks, we don't have ReLU activations here because input and output neurons do not have ReLUs. So if you think again about this representation as a composition of affine functions and ReLUs, we have an affine function here and an affine function here and no ReLU in between. So they just combine into one big affine function. So this is not actually a layer in our neural network. In other words, that means that to compute a maximum of four numbers, we just need two hidden layers here. So, and if you think about this, what it means more generally, it means that with one additional hidden layer, you can double the number of numbers you take the maximum of by just inductively stacking this construction again and again. Or if we put it the other way around, if we want to compute the maximum of n numbers with this construction, we can do this with a logarithmic number of hidden layers. Okay, so far so good. Questions about this example?
I have a question.
Yes.
Is this somehow best possible, like a
Yeah, you're taking away what's going to come. I mean, the short answer is I don't know, but I will talk about this a lot in the next 15 minutes or so.
Okay.
Okay, so before we talk about this question more generally, let's first generalize our view on the set of functions. I mean, so far we just looked at one cute example, this maximum function. But what about general functions? What functions can we express at all with a ReLU neural network? And the first observation is, okay, if you represent a function, it will certainly be continuous and piecewise linear, because every ReLU neuron computes a continuous and piecewise linear function, and if you compose them, you will maintain these properties. And now the cool thing is that that's actually the full characterization. So if you have a continuous and piecewise linear function, you can actually represent it with a ReLU neural network. And in fact, a logarithmic number of hidden layers is sufficient for that. And how do you prove this? Basically, you reduce like an arbitrary continuous piecewise linear function like this, for example. You write it as a big linear combination of maxima functions, and you just use the construction I just showed you. And that's also why you obtain this logarithmic upper bound. It just comes from the maximum function, and all the maximum computations you do in this representation will be in parallel, so you still just have a logarithmic number of hidden layers. But the width can be pretty large if your function is very complex. Okay, so that's cool. We now know what's possible at all with ReLU neural networks. And now the obvious two questions are like the one that was already asked. I mean, is this logarithmic depth best possible? Or are there functions where or can we maybe always be better? Or are there functions where we really need these logarithmically many layers? And the other question is more about the size of the neural network. And okay, if you think in terms of complexity theory, then you always wonder what's possible with polynomial complexities. So in case of neural networks, it would be what's possible with polynomial-size neural networks. Okay, so these are the two questions I would like to talk about. And let's start with the logarithmic depth question. So is logarithmic depth the best we can do for general continuous piecewise linear functions, but also for the maximum function? And the maximum function is, in fact, not just a cute little example. Let me first state what I believe, but it's just a conjecture and not more than that. So I believe that this logarithmic upper bound is tight, and we actually also have a lower bound that matches this upper bound. And as I said, the maximum function is not just a cute little example, and the reason is basically the proof idea I explained earlier to you. So if you have a general continuous piecewise linear function, you can write it as a linear combination of maxima functions. But in other words, that means that kind of the maximum function is the most difficult function for a neural network in terms of depth. And then if you do all the technical details, you can actually figure out that this conjecture is really equivalent to just investigating the maximum function. And the interesting cases, since we are talking about a logarithm here, are always when you take a maximum of a power of 2 plus 1 many numbers, and without loss of generality, you can set one of them to 0 to make the function as simple as possible, basically. So the interesting cases are exactly the maximum of 0 and 2 to the k variables. And then we wonder, can we represent this with k hidden layers, which is a logarithm of 2 to the k? And yeah, the conjecture is we cannot. And yeah, so I mean, the initial conjecture sounded very complicated. It's more like, okay, we want to say something about all continuous piecewise linear functions. We have no clue what they look like. But now this conjecture talks about a very specific function, and it's kind of curious that they are actually equivalent. And now I mean, yeah, in the first moment, I would be much more optimistic that now we can prove something. So let's see what we know about this. Yes, there's a question.
Can I ask a question? Yeah, sorry. I'm not sure if someone's asking a question. This is not, okay, it's not clear to me. So you're basically saying that this, the first conjecture actually reduces to the second conjecture. Is that, I mean, I don't see how that's obvious. It seems non-trivial here.
No, it's not obvious. What you need is this representation theorem for continuous piecewise linear functions which says that every continuous piecewise linear function can be represented as a linear combination of maxima of not too many terms.
Okay. Okay.
If you
Okay.
use this, then you see that, okay, if there was any example that needs logarithmically many hidden layers, since
Yeah.
that example you can write in this representation, it also means that for the maximum you need logarithmically many layers.
Mm, mm.
That's the
Okay.
high-level idea behind that.
Okay. 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 Thank you.
You're welcome. Any other question?
Maybe so you here the width of the network is always unlimited, right?
Yes, right now we don't care about width at all.
Yeah. So what's the so what's the relation to universality here? The universality theorem.
Yeah, I guess the big difference is that we are talking about exact representations. So if you are happy with approximations and you are happy with restricting yourself to a bounded domain, that's another thing that's always done in universal approximation theorems, then one hidden layer would be sufficient by universal approximation theorems. Yeah, but you have these two restrictions. And also for these universal approximation theorems, if your function is complicated, you also need very large width, actually.
Thank you.
You're welcome. Okay, so now let's talk about what's known about this simplified version of the conjecture. And the first thing that's known is not too difficult. It is that the special case of k equals 1, so one hidden layer, and maximum of 0, x1, and x2, the conjecture is true, so we cannot represent this function with one hidden layer. So the function looks like this. You have three regions, one region where 0 is maximum, one region where x1 is maximum, and one region where x2 is maximum. And if your neural network looks like this, it won't be sufficient to compute this function. And that's not too difficult to prove. That's basically, if you remember this 3D picture I showed in the beginning, every neuron computes something that has two regions, one zero region and one non-zero region, and the boundary is a hyperplane or a line in 2D. So the function, all the regions should be size of a hyperplane arrangement, but this is not the case in this example. That's the reason why it doesn't work. Okay, so that's the first base case. What else do we know? And the answer is basically nothing. So no other case. There's no other lower bound than one hidden layer is not sufficient for this function. And I mean, still my talk doesn't end here, so I have something more to tell you. But first let's think what that means. It means that we don't know any function for which we can prove that we need more than two hidden layers. So it might be, so far, that every continuous piecewise linear function can be represented with two hidden layers. So there's a gap between two, which is the best possible lower bound given through this example, and logarithm of n, basically, which is the upper bound we saw earlier. And the first function where we don't know how many hidden layers we need is the maximum of 5 numbers, or the maximum of 4 numbers in 0. Okay, so if that's basically everything we know, what can we still do? I mean, yeah, what can you do if you don't know how to prove something? You can make further assumptions that make it easier to prove. So, for example, let me define what I mean with a nice neural network. And I can also explain why I think this is nice. So a nice neural network to compute, so you always need to think that we want to compute the maximum function. So the maximum function should somehow be invariant as long as the order of the inputs doesn't change, right? So the idea would be that in our neural network, the linear regions don't they don't interrupt within one of these regions. So if you look at the whole space and you subdivide it into all the permutations of the inputs, then you obtain like a hyperplane arrangement like this. And then you look at all the cells. Now the idea would be our neural network to compute the maximum function is nice if it is linear within each of these like conic cells we have in this hyperplane arrangement. And if you look at the upper bound construction that I showed you earlier, this is actually a nice neural network. Okay, so the intuition would be we don't need breakpoints within these regions of this hyperplane arrangement. All linear regions would be like unions of these cells. Also in higher dimensions, I mean, in 2 dimensions, it doesn't look too interesting. It's just these 6 regions. But if you have more dimensions, these are quite some regions already. Okay. And for nice neural networks, there are 2 results. One, which is basically my first result I did in this area, and one which is my most recent result I did in this area. So the first thing we were able to show is that for nice neural networks, we can actually prove that 2 hidden layers are not sufficient to compute the maximum of 5 numbers. So the next example that was open is actually proven for nice neural networks here. And we did that like with an extensive computation. So it was a computer-aided proof, actually. And then the other most recent result is that we got rid of this computer aid and we were able to do something more general, which gives us at least a non-constant lower bound, but it's doubly logarithmic, unfortunately. So nice neural networks need log n hidden layers to compute the maximum of n numbers. And that was actually like it's a very, very deep into combinatorics and polyhedral stuff, this result. So Moritz Grillo is a PhD student at TU Berlin, and he worked hard to make this work. Okay, so this is like one set of results, and then there's a third result I have about this question, and this is, I think, the result I like the most because it has a really polyhedral, nice polyhedral geometric proof. And this has nothing to do with nice neural networks now, but it has to do with neural networks where we restrict all the weights to be integer, which, if you remember in the construction for the maximum I showed you earlier, all the weights were integers. So this also, these neural networks satisfy this assumption. And in this case, you can actually prove the lower bound that matches the upper bound. So we need logarithmically many hidden layers if we restrict ourselves to integer weights. And that really is a nice geometric proof using polyhedra. And I would like to at least give you the first step for this proof. But first, are there any questions about the results?
Maybe one question. So you have this result that if you restrict to nice neural networks, then you have lower bounds.
Yes.
So my question is basically the max function itself is nice, right?
Yes. Of course. Otherwise, it wouldn't make sense to restrict to nice neural networks, obviously.
Yes. So if you want to represent a nice function with a neural network, and it should be the representation should be exact. How could the network then not be nice?
Like, so for the neural network being nice, we require
each neuron.
By each neuron.
Okay.
Nice. It could be helpful that some neuron does something weird within the region, but then this cancels out with some other neuron, and then you do something that does not affect like the interior of a region anymore, but it somehow changes what happens between the regions.
Okay.
And this, I mean, intuitively, you wouldn't know why you should need something like this, but we also wouldn't know how to prove that you don't need it. Yeah, each neuron, that's important. Yeah, I should have stressed this more. Okay. So here's how you use polyhedra. And that works via a nice duality statement. So neural networks compute continuous and piecewise linear functions. And one of these functions is just a maximum of 0, x1, and x2. So let's look at this example. And now you can, if you have a continuous and piecewise linear function that is, let's say it is convex, like this function, it is convex, you can associate a polyhedron with that, a polytope actually. And how do you do that? You look at the coefficient vectors of all the linear functions computed at the regions. So at this region, we compute the function 0, and we are in R2, so the coefficient vector is 0, 0. This is this point. In this region, we compute the function x1, so the coefficient vector is 1, 0, which is this point. And in this region, we compute the coefficient vector 0. We compute the function x1, which has coefficient vector 0, 1, which is this point. And then we take the convex hull of these, like of all the points corresponding to all the regions, and we obtain a polytope. And if you have heard of tropical geometry, then you might have seen this construction, and you would know it under the name Newton polytope of this function, which can be seen as a tropical polynomial. If you don't know tropical geometry, then just don't care. Just remember that this is called the Newton polytope. And the other direction also works. So if you have a polytope, you can reconstruct your original function. What can you do? Basically, you look at all the objective directions you could optimize a linear function over this polytope. So, I don't know. Think about linear optimization and think about, okay, I want to optimize in some direction, what would be the objective value? And if you do that and you know some linear programming, you would know that the optimal solution would always be vertex. And as long as the optimal solution is the same vertex, the objective function would be just the linear function defined by that vertex. And if you think about it, you see that it just recovers exactly what we did before the other direction. So it gives you, like, the function that maps the objective direction to the objective value would exactly be the continuous piecewise linear function we started with. And this is something that's known in like optimization or convex analysis, and it's called the support function of a convex body, and in particular of a polytope. And that would be always, like for polytopes, it always would be a continuous and piecewise linear function. And that way we can have like an isomorphism between these two types of objects, actually. And I say isomorphism because it's actually compatible with a bunch of nice operations. What are these operations? Well, if you scale up the function by a positive scalar, you basically scale up the coefficients, so you just scale up the polytope by the same scalar. If you add two functions, then, okay, this requires a bit more thought, but it's still not too difficult to see that this corresponds to the Minkowski sum of the corresponding polytopes. So what is a Minkowski sum? A Minkowski sum of two polytopes would just be the like the set of points that can be represented as the sum of a point in one polytope and the point in the other polytope. And the third operation is if you take the maximum of two of these continuous piecewise linear functions, that actually corresponds to taking the convex hull. Any questions about this duality perspective? Okay. So how can we now use this duality to prove something about neural networks? Basically, instead of studying directly the functions computed by the neural network, we study the Newton polytopes associated with these functions. And what does it mean? Well, for example, what you can prove is that all the polytopes associated with a one hidden layer neural network will be centrally symmetric. But this polytope is not centrally symmetric, which implies that, like the result I mentioned earlier, this function cannot be computed by a one hidden layer neural network. That's like an alternative way of proving that. I earlier explained this with a hyperplane arrangement and stuff, but you can also prove it with Newton polytopes this way. And the same way, you can try to find invariants of polytopes that are associated with neural networks with a certain number of layers and compare that with the polytope you would like to express, and that way prove lower bounds on neural networks. And that's basically the underlying idea behind this result about integer weights that I showed you earlier. Okay, questions about this? Otherwise, I would conclude with the part about the logarithmic depth. I don't think I would be able to go more into the proof details here and use the remaining few minutes to talk about polynomial size neural networks. And here I would like to start by mentioning some positive results. I mean, if you think about what's possible with polynomial complexity, well, the first thing you should do is to compare it with other, maybe more standard models of computation. And since I have a combinatorial optimization background, a very natural thing for me was to look at combinatorial optimization problems for which we know we can solve them in polynomial time and see if we can also solve them with polynomial size neural networks. And this was actually more tricky than I thought in the beginning because a neural network can basically only do two things. It can compute maxima and linear transformations, and that's it, more or less. So if you want to prove that some problem can be solved with such a neural network, you need to find an algorithm that only uses maxima and linear transformations. And if you think about most algorithms, well, if you have a nice dynamic program, then sometimes that's the case. But in most algorithms, you know from your basic algorithm course, I guess, I mean, there are some funny if branchings or stuff like that. And all this you simply can't do with a neural network. So in the end, it was actually quite some effort to prove these two positive results, saying that if you have, let's say, a graph, and you have some edge weights, and you want to put these edge weights into a neural network that computes the value of a minimum spanning tree in the graph, this can be done by a polynomial size neural network. And same for the maximum flow problem, actually. Okay. So here are positive results, but maybe from everything I've told you so far in this talk, you may have realized that I usually like negative results more than positive results. So what can we say about this? Or first, if you think more about positive results, what about other problems you can solve in polynomial time, like matchings or minimum cost flows or general linear programs even? And then, well, if you don't believe that this would be possible, then what would be ways to find lower bounds? And thinking about combinatorial optimization problems, well, proving lower bounds is usually difficult. Even like sometimes you can prove NP hardness of a problem, but maybe there are some other ways. And actually, yes, there's some notion which has been used in combinatorial optimization to prove lower bounds in the context of linear programming, actually. So what is this notion? It's called extension complexity of a polytope. And what is the extension complexity? Well, look at this polytope down here, which is an octagon. It's like, yeah, a 2D polytope with 8 facets. So if you want to represent this with a linear program, you need 8 inequalities to represent it, 1 for each facet. Now, the funny thing is, this octagon is actually the projection of this 3-dimensional polytope. You can, yeah, stare at it a bit, and then you see that it is actually the projection. And this 3-dimensional polytope has only 6 facets. So you can represent this with 6 inequalities. But you need 3 variables now, of course, because we are in 3D. So what is the takeaway? The takeaway is that sometimes, if you want to find a linear programming formulation for a polytope, it helps to introduce extra variables because then you can have fewer inequalities. And now, if you want to find the best linear programming formulation for a polytope, what you need to wonder is what's actually the polytope with the fewest facets that projects to my polytope. And this is exactly the extension complexity. So the fewest number of facets of any polytope that projects to the polytope in question, that would be the extension complexity of the polytope. And that actually captures the minimum size of a linear programming formulation for that polytope. And what people have proven is that for certain polytopes that correspond to certain combinatorial optimization problems, like the matching problem, for example, but also NP-hard problems like the TSP problem, the associated polytopes have exponential extension complexity. So if you want to solve them with a linear programming computation, you need exponentially many inequalities. So you cannot get a polynomial size algorithm that way. For the TSP problem, that's cool because we know it's NP-hard, but this gives you an unconditional lower bound. It doesn't depend on P is not equal to NP. But on the downside is it doesn't say something about general algorithms, it just says something about LP computations. And for the matching polytope, that's even more surprising because for that we know we can solve the problem in polynomial time, but apparently not with a single linear programming computation. And now the vision would be to use these strong celebrated lower bound results for the extension complexity to also say something about the size of neural networks. And that way we could, for example, find a problem like matching, which we can solve in polynomial time, but maybe not with a polynomial size neural network. So that's the idea. Okay. So let's say it's not only the idea, let's say that's the dream, because I like lower bounds so much that I dream of them. And then let's define xc of P as the extension complexity of a polytope P, and neural network complexity of P as the number of neurons required to compute the support function of the polytope P with a neural network. And then the dream result would be that we can bound the extension complexity polynomially in the neural network complexity, which then would imply that if the extension complexity is exponential, then also the neural network associated with that polytope would be exponential size. That would be the dream result, but so far it's just a dream, unfortunately. And again, as I said earlier, when I don't know how to solve something, what do? Well, you weaken your dream to still make it true. And there are two ways in which we did that. The one way of weakening this inequality is you restrict the class of neural networks you're talking about. And yeah, so we proved that the dream is actually true if you restrict to monotone or input convex neural networks. These are neural networks where you say that either all or some weights need to be non-negative, which makes sense in some applications where you want to enforce the function of your neural network to be convex or something like that. And in this case, the dream is true, and you can actually transfer extension complexity results to neural networks. And then what you can also do instead is you still talk about general neural networks, but you strengthen the notion of extension complexity. You basically make the left-hand side of the inequality smaller, which also makes the dream easier to prove. And we did that too, leading to a generalized version of extension complexity that might be interesting for the combinatorial optimization community. And in this case, also the dream becomes true. But in particular, the first point of this theorem implies that monotone and input convex neural networks need to be exponential if they want to solve problems like matching and TSP and so on. Yeah, that's it, what I want to talk about for the polynomial size. Before I conclude the talk, let's maybe ask if you have questions for this specifically.
I have a question.
Yeah.
So for the lifts of polytopes, it's something to do with the rank of the what is known as the slack matrix. Is there a notion of a slack matrix for in this context for like ReLU networks?
Yeah. I mean,
Or do you have an idea? I don't know. Yeah, I guess because once you identify this thing, then you just have to compute the rank in principle. But I have no idea if this is a reasonable roadmap.
Well, it's definitely something you need to think about. I mean,
Yeah.
like the way we proved our weak versions of the dream is basically we took our neural network and we constructed an explicit extended formulation for the corresponding polytope.
Okay.
If you want to talk,
Okay.
but this only works for these monotone and input convex neural networks.
Mhm,
And if you
mhm.
want to talk about general neural networks, then you need to generalize this notion of extension complexity, as I said, and then you basically look at differences of polytopes in some weird sense of differences, and then you basically have two Slack matrices associated with them. And then the question is there a unified version of non-negative rank of these two Slack matrices or something like that? And we thought about this, but we don't have a good answer at this point.
Okay. Interesting. Sorry, it's a tough question.
No,
Yeah.
I mean, yeah, but it's exactly the right question to ask if you want to solve this dream in general, I guess.
Yeah.
And I mean, all this non-negative rank business is what basically made these breakthrough results
Yeah.
about the extension complexity possible.
Yeah.
Yeah. And I guess, I mean, if you really want to solve this, what you need to do is you need to go into these lower bound proofs for extension complexity, and which are very complicated, and need to see what you can rescue for the neural network case.
Yeah, this seems tough. Man. Thanks.
You're welcome. Very good question. Thanks. Okay, so let me conclude the talk basically by just two small takeaways. The first one is polyhedra, a nice tool to understand neural networks. And the second one is, well, basically I wrote a lot of papers about problems I haven't solved. So all the big problems are still open and you're very welcome to join solving them. And yeah, so I would like to thank you with this nice duality picture between continuous piecewise linear functions and polytopes.
Thank you very much, Christoph. We had quite a lot of questions during the talk, but are there still any questions from the audience?
Yes, I would like to ask a question. I don't know if you see me. Maybe.
Now I do.
Hello, nice talk. Thank you.
Thank you.
I wanted to ask a question, which is more like a general thing that I've been thinking about a little bit. So when you explain this duality, on both sides, what you get, you can see it as an algebra over the tropical numbers, as a semi-ring algebra.
Yeah.
Is there anyone that tried to approach any of these problems by studying some property of these algebras?
Okay. So my perspective on this, I'm not sure if like people doing algebra would agree, but my perspective on this is just like a lot, like many different languages for the same thing. Basically.
Yeah.
So yeah, I don't know if I have a good answer.
Because I was just thinking now, and I think it doesn't work, but I was thinking like if I consider for example, the semi-ring of this piecewise linear functions, then I can say, okay, can I cut out in some algebraic way the subsets that are realized by a specific architecture? But I don't think this is an algebraic. I mean, I cannot say like it's a sub-algebra or something like this, for example.
Yeah,
So,
I guess usually if you try to like relate these neural network questions to like purely algebraic questions, usually like depending how you exactly do the relation, one of the two operations you can do with a neural network is always weird in the algebraic setting. So
yeah, exactly, yes.
Either you do something that is very compatible with Minkowski sums, but then this convex hull operation is really weird and messes up everything. Or you do something that behaves nicely with the convex hull operation, but then the Minkowski sum is really weird and messes up everything. So
yeah, because actually exactly what I was thinking was like, if I take two functions that are realized by the same neural network, if I'm not wrong, in general, I can always bound the number of monomials appearing in a representation as a polynomial, for example, as a ratio of polynomials. There should be some results by Loho, Brandenburg,
yeah.
Yes, exactly.
Yeah.
So, but then if I take the sum of these two, then I think this doesn't respect that bound in general, right? So already that shouldn't be, you should tell me that these functions are not, for example, closed with respect to sum or something like that. So yeah, I think what you say is right. I mean, this is an example of what you said.
Yeah, I think what you say makes sense to me. I think I would agree.
Okay, thanks.
You're welcome.
Thank you. Unless there are more questions, then please just interrupt me. But it does not seem to be so. So let's thank the speaker again for the very nice talk.
Yeah, thank you for being an active audience. It was
Yeah. And see you next time.